and this is one of them. Frei Otto joins his great predecessors, Frank Lloyd Wright, who's lectured here, and Le Corbusier, and is addressing us today on fundamental architectural and philosophical ideas. However, there is something quite different and special in Frei's relationship with the AA that the others didn't have. He was part of the team that created the buildings at Hook Park, which now belong to the AA. When I say part of the team, he's joined by other members of the team, his daughter, Christina, who's sitting, his wife, of course, who's a great supporter, and myself, who was the architect with Frei. There were other members of the team, and the late Ted Happold, the great engineer, and Michael Dixon of Happolds. Now, Christina will be giving workshops at Hook on Friday and Saturday of this week. She gives the MIDA workshops. And it is wonderful that the whole family is here. Thank you for coming. Moisen is devastated that he can't be here tonight to hear you speak, Frei, and share your thoughts. He asked me to say on his behalf that he is in Geneva working on the Aga Khan jury. However, as many of you know, Hook is very, very close to his heart, and he hopes you, Frei, and Christina will participate with us to create an extraordinary place in the future. So, we welcome you here tonight, Frei Otto. Your architecture, which spans from the buildings for the Munich Olympics to the project for the Stuttgart railway station today, we salute your way of thinking, which has affected our recent past and is central to our future. Frei Otto.
Could we shut it up?
The light.
Mm. My dear friends in London, ladies and gentlemen, it is, I think, the fourth or fifth time that I speak here on the school, and always my heart has something to do with the AA. I really do not know how I should make this evening, but I will try it, and I hope that my slides, you could see them in this special room. It is, for me, I have always to wait some 5 minutes to get back to the English language. It's not my mother language. And I feel I have a terrible accent, but please pardon me. I'm an architect, not an engineer, as many things, but I always was interested in a good relationship between architects and engineers, and I think it's very, very important. Our profession is driving apart, and especially handscrafting and all these things are now in a problematic situation. Some people think that they only could sit behind a computer and making design. I know that design is done in our brain, and the sketch is the first thing which is coming out, and that what we are thinking in our brain, how we can bring it into nature is one point, but also how we can study the nature so that we can be a part of her. And I think that the architects should be helpers for man, that man can live on the surface of earth. They must help to that catastrophe cannot kill people. That's quite simple, but it's very much necessary, because until now we have these big catastrophes of non-living nature killing us, but the biggest enemy of building is man. And I have seen in the last wars cities burning, and that is not a nice view. And these are men destroying houses, destroying cities. And when we started to rebuild our country, other countries, Middle Europe, we always were thinking that there is no building which can be stable for centuries or longer. Buildings must always change to be perfect. And also people should die when their time is over, but die with excellency. But some of buildings should be protected because they should show what people has been done and should be a help that man can go into the future. All these I will try to tell you, and let's go ahead. Could I have my first picture? Well, it was after my last lecture here. We did sit together in a restaurant, and so the idea was born that an object on which we worked together, Richard Burton, Ted Happold, and myself, and many others from our teams, for John Makepeace to create a school to use wood. And it was Richard, I think it was you, to make this drawing on the left side. It's a little bit out of focus, please pardon it. And on the right side is one of our first models to make a workshop, a central building, and some houses for people which are living there. Next picture, please. And some models which we studied. On the left side was a central building, and just a tent out of wood, because we said that we could use those wet trees. The forest was planted, I think, 56, and the trees did grow to a height of between 12 and 15 meters, very thin, and we tried to use and to make buildings out of wet wood, where the wood should be drying in the building. As an experiment, because we had not the time to wait that these trees could be dry by themselves. Next pictures. This is the so-called master house. It is hanging trees from the ridge. On the right side, we studied the model on the side. If you have a little model, you should go to the side and to look where the best side it is. The side was beautiful. We remember the day when it was the first time on the side. The ground was blue, from blue bells. It was really beautiful. Next picture. This is now the ready building. How you call it, master house, or I don't know what is the official name now of the house. There's no official name, but some of you are going tomorrow to Hook Park and will see it. I have not seen it now for many years. I hope it's still existing. Next picture, please. And for the workshop, we made models out of very thin stainless or brass bars, studying the shape. Later on, I used once more these experiments for the World's Fair in Hanover last year. There was a young Japanese architect. He's now pretty much known, Shigeru Ban, and we made the building together. But before we made Hook Park, next picture please. And it was like this. You see the very thin members. We studied, of course, how they could be arches on the right side. We pulled them down and to make a grid shell out of wooden arches, bending it just by power. Next picture. And this is then the workshop building. We covered it with a tensile membrane out of polyester and is PVC coated. Next picture. And I will tell a little bit about modeling and how to bring out of models buildings. These tests I made 1958 with my class at Washington University in St. Louis, USA, showing a rubber membrane loaded with nails, and later on converted and to make it as a shell under compression. We call all these structures shells without bending. They are related to old vaults, which were invented long before the Romans. Next picture. My largest building was the so-called Multihalle in Mannheim, done together with the architect Mutschler and Langner in Germany. The engineers had been of Arab and Partners in the time where Ted Hepburn was the leader of the so-called Structure 3, the kind of a fire police for problematic projects. But it happened that Old of Arab asked me, if you will do a building like this, I would like to do it. And it happened that the German engineer, which we had on site and we should use him, said that it is too much for me. I have not the courage to build this building. And I think it is a problematic building because the span is more than 80 meters and the wood is very thin. There are lattices of long grain wood. The hemlock pine of Canada we used, and the lattices are 47 to 40 millimeters, not centimeters. And I said that we could build a building just with the lattice of the roof without the structures underneath. So we did it. And we are happy the building is standing still. It was planned only for one summer. It's now a protected building. Next picture. And we learned very much. It was an exhibition, so-called, I can't translate it, Gesamtkunstwerk. A total art piece was the name of the exhibition by a Swiss art director. And I was asked to reconstruct the model which Antoni Gaudi built in the 20s of last century, but the model was destroyed 1936 in the Civil War of Spain and completely lost. Nothing remained of this model, but only 21 photographs did exist, and using the method of stereoscopic reconstructing a building, we did the model of Gaudi once more. And now we have not only 21 photographs, but many more, and we even could see more, as everyone did know. You see the model is on the left side. And you see in a mirror the standing object. The object is the chapel in the Parc Güell in Barcelona. And on the right side, it is a photograph inside the model, and with some fantasy you will see how the chapel in Güell would have been looked if Gaudi would have built it. The model stands now in the basement in the Museum of Gaudi in the Sagrada Familia. Of course, I did not the whole thing with my own hands. It was specially done with the Dutch group around Jan Mollema and Jos Tomlo. Jos Tomlo is now professor in East Germany, and Jan Mollema in, I think, in Rotterdam. Next picture. Of course, if you have any questions to these things, please ask, that we could start a little bit discussion. I would be happy if you could do it, so I know. Our largest project on which we are working in my office since 6 years, the architect is Christoph Ingenhofen. He was invited to the competition for the station in Stuttgart. The station in Stuttgart was built in the 20s by Paul Bonatz. He was a hero of the Stuttgart school. And the trains are on the upper level. It's a so-called end station. And this station should be turned in a, I don't have the English word, going through station, which is in a right angle. And on the right side you see our design for the competition to be underneath 12 meters under the ground, and to have open holes which are supported by columns. And I offered to Christoph Ingenhofen, firstly the engineer, of course, the Bureau Herpold, and especially involved is Michael Dixon and now also Ian Little, and joined them together with Fritz Leonard, the very well-known German engineer. Maybe you know he invented the concrete television towers and built many suspension bridges. So, but next picture. But how to solve the question? I give some sketches because the railroad station is only between 9 and 12 meters underground. It is 430 meters long, nearly 100 meters wide, and had only a room between the surface of earth and streets of these 9 to 12 meters. Very important is now how thick you could make the ceiling, which should be planted, because the room is going away. And so I remember, if you will make a big concrete plate, it should be there nearly 2 meters thick. If you put your column so far away, we decided that it is necessary that the columns are about 34 meters away. And it's nothing. It should be a very, very flat space. It would be the largest space of the city of Stuttgart. Stuttgart has about 600,000 inhabitants, but all around are about 2 million in the so-called outer region. And I remembered, and the question is always how good are now the knowledge of the engineers. And we know that to calculate reinforced concrete, it is somewhat, I will not say superficial, it is very good for normal buildings of small span. But for longer span, there are problems, because normal concrete always will break. You can, of course, pre-tension it, but pre-tensioning, you can then bring the 2 meters down to maybe 1.50 meters, but not more. And the calculation shows you, and you are calculating with the elastic theory, but there is another way of calculating it. I show you on the left picture. If you put all concrete away, which is not in compression, then you will have a two-dimensional thin shell in the concrete. And you could also calculate it in a way which is shown on the left side. But still, then you would have the tension members 2 meters underneath, and we also could not use these tension members. On the right-hand sketch, you see those many possibilities which we had to solve this incredible equation, and just to dig a valley. The valley will be filled with groundwater in a few minutes, because the railroad is just crossing a little stream. There is just a stream which is mm, going out of Stuttgart. Stuttgart is a huge funnel, and there are big water sometimes in rainstorms. But so the first upper line was what we did at first to make this valley and to hang over the valley a tension structure. But then we started also because the client wanted a section which is under the second sketch there. But we studied then all different ways, and we are still studying because it may need 2 further years before the building will be started, and it will be not been ready before nearly 1920. It's a very, very difficult question, and I do not know if I would see the building. Next picture. And to show for the first step, of course, you always are using things which you have done. So I was thinking for the railroad station Stuttgart to use a cable net, which I have done for this building. Next picture, it is the Montreal Pavilion. Or for the Olympics, we have had a cable net, and we studied also to use the cable net and to plant it. Next picture. And this solution was coming out at the beginning, but we have had only 3 months' time for the competition. You see the cable net, and this would be then the structure. Underneath of the point will be a mast, and I tried also to reduce the railroad station. That's for 6 lanes, but we have to build it now with 8 lanes. Next picture. Then we studied the so-called hydrostatic shell. And in the ground, and you know it from the London subways, that the best shape of a tunnel in groundwater especially, and we are here in groundwater, is the shape of a tube or a fire hose which is filled with water. This is the so-called water shape, and you can reverse this into a shell and you are getting out shapes like this. Of course, they are difficult to calculate. Next picture. Next, please. We have done it. We have been invited by Italian friends and architects for a competition for the railroad station in Florence. And we offered such a hydrostatic shell, but this is much lower. It is about 24 meters below the city of Florence. The tunnels are driven just underneath of the city. But it is possible now to calculate it, to do models and to calculate it, and also the groundwater flow is above the tunnel, under between gravel, and we should not destroy it because the plans of the Italian was just to make a big caisson, and they stopped all groundwater. It will get an ecological problem. Next picture. But once more back to Stuttgart. If we have to solve this problem with a kind of a shell. We have once more to study what is a shell, what is an arch. And since Hooke, the famous physicist and mathematician, we know that we can invert a hanging chain into a self-standing arch, or a grid of chains into a standing shell. As I have shown you with the Nervi model, Nervi used this method just 100 years ago, but before was a German architect for the city of Karlsruhe and many others, but no one has proved, is this idea, I take a chain and let them stand, and the standing arch in the best shape is exactly like the hanging chain. So I use those methods which I have had at my Institute of Lightweight Structures in Stuttgart, and we made tests, built it exactly as arch, even also under load on the right side. I could prove that this is correct, but we could not 100% exactly tell that Hooke and Newton have had the right thing. You know a little bit that the structure of St. Paul's Cathedral here in London was following this way, and there are 3 domes above each other, and the really one which is taking the load is the cone shell out of stones in St. Paul's. Next picture. When we made these studies, automatically we did come also to us a shape, and here we invented an S-curve arch for maybe to go over the water. Very often a street will move from one side of the stream to another one, and automatically you need an arch which is in floor plan an S-curve. And also we made the design for a bridge which has a floor plan which is more like an U. Next picture. And in this way, to make a shell without bending, and a shell without bending is always a volt, especially out of concrete. It starts to break and it's out of stone. And the oldest method to make it is a so-called cross volt, which is standing. This little model is standing without collapsing, but it's out of wooden stones. It doesn't matter if you make the model out of wood or stone or lead. You can use all materials, because to get the shape, the material is, you have the material completely free. Only when the material is too flexible, then it could collapse a little bit earlier. On the right side, this is the oldest method to make roofs or walls with stone, the so-called laid, the free laid dome. It is even not necessary that the stones can be together. The friction is enough. I was many years ago on the Shetland Islands, and I discovered that about 2 or 3,000 years before Christ, these kind of domes had been built, and it means 5,000 years ago, in the Shetlands. They are now broken, but the basement is still existing. Very interesting how early people in your country have started to make these buildings. Next picture. But we are still on the railroad station Stuttgart. How to do it? To combine an air hole that air and light can come into this huge space. Believe what are 100 meters to 430 meters. And we made this model on the left side. The model was hanging out of a very thin woven material like a rail, and then powdered with plaster, and then in a dust of water, and the plaster will get hard, and this model was coming out. Always we try not too much to manipulate, just to discover those shapes which will come out by themselves. It was the model where we then, in the team of architects and engineers, decide we will go this way for the competition. Next picture. But how to put the columns? Should we use like the model? Of course, the model we just take a square grid. We are a society of right angles, a Cartesian society, right angle, right angle. But if you want to test how the columns should be stand so that every column is taking the best space, we invented a method which is this one. We take little needles, make them magnetic, put a little point of styrofoam on there, and if the magnetic forces are parallel, so that always one pole is above and the other one below, then they have the tendency to swim apart. And if you have a closed frame in water, they fill this frame in the best possible way. One experiment of the right side, the big dot in the middle is always the needle, and you see they have a kind of triangular grid. And the land which they, or the water what they are using are then more hexagons. And we invent another method to make to bring a little method in that other pieces are joining together. And if you have a very thin styrofoam and you pull it on water, then they start to pull together, just vice versa than the magnetic needles. And with this play you could study cities and how man is covering earth, all the earth which are higher animals are using, like eagles or foxes. And we made these studies also. I developed it much earlier, and did then change the position of the columns. Next picture. And we made then the columns in hexagon grid. This is a calculation on the left side, a so-called minimal surface calculation by friends of mine, which have been my students, Bodo Rasch in Stuttgart and Jürgen Bradac, and the inventor of this method of calculation is Eberhard Haug. It's called the LISA. And you are getting out the same thing as on the right side. On the right side is a soap bubble. And in the soap bubble, if you put a little hair inside and put the soap and destroy the soap bubble in the middle, then you get a exact round circle. But if you pull on one point in the circle, you get a shape like this. I use the shape for many buildings. I have shown you our Montreal pavilion, and also for the Olympics in Munich, also for my institute. You get a wonderful curve. This curve, which you see on the right side, around the hole, is a peculiar line. It is a line in space with only one radius of curvature. Has exactly only one radius of curvature, but not a circle, but the line starts here, is going around, and is coming back, and to the point where the forces are meeting, it is in space a curve with one curvature. You know another famous one, it's a spiral line. Maybe you could use it as a spiral stair. Next picture. And we use then this line, and you see how the holes are now put in order, but a little bit disturbed because they should stand in the middle between the rails, so that people can good see it. And from a certain line it looks nearly like a circle, but it is a circle in space. Next picture. And this was the answer, and with this model we did win the competition. And we are, of course, happy, but then the big work started. And so we are now, we will not believe it, 6 years on work. Next picture. This was a railroad station, Stuttgart. Now, it is just 5 weeks ago, we could open a bridge, 2 new bridges, which we built, and I show you a little bit the history. It's a footwalk bridge, 120 meters long, but the story was always you could use straight bars to solve some structural problems. I use them for a so-called hump tent, which we built in 1957 with a great tent maker, and Peter Strohmeyer, a tent which is curved like this with straight bars to connect the canvas with a pole. But be careful in the point when we wanted to erect the tent, it did collapse, because it did turn this point, and so we had to make the little funnel underneath. The collapse was not a problem. The tent was only 24 meters spanning, and very, very light, and my friend Ewald Bubner did direct it and nothing happened. But then for another building on the right side, I had a grant from the German government, the Minister for Research, to develop a new runway or a new Fahrweg in German, way for the German magnetic railway. I think you are calling it a maglev. And this should be better and also should have better aesthetics. I did this work together with the team of Ted Heppold. He by himself was very much interested in this type of structure. One of the results is the right one, but we made several proposals. Of course, it was going not out of the Ministry of Research, and so maybe the ministers for the railways did never know what we did. This is typical in many countries, I think also in yours. And next picture. But the bridge which we opened just is similar. The model is on the left side, and on the right side is the execution. We made a new trial. We did not build the bridge out of steel tubes, but out of steel bars, full bars of 70 millimeter thickness. And the whole bridge is only clamped with a special clamp, only one clamp, but which is turned, and all the bridge is zinc coated. As I said, 130 meters long over a street. You see the street will be enlarged on the right side. It's still small. And over a little stream behind. And in a slope. Next picture. These are details. We developed also the clamp with 4 screws. Next picture, please. It looks on the right side pretty large, but 70 millimeters are really not. It's just like this. The bridge is very, very stiff. Only those bars which are above the walkways, they have a light tendency to swing, but under the footwalking, the bridge is moving nearly nothing. And I wanted that it's only clamped, but the engineers, this time once more, Bureau Heppold together with Bureau Hilbers in Berlin, we all wanted only to be clamped, but then we have had a proof engineer, and the proof engineer should understand also, but sometimes if you don't understand, he was demanding. And so some of the points has been a lash which is velvet, which I don't like. But normally the bridge is only screwed. And next picture. I'm coming now to another method of design, which was also developed out of models, this so-called tree construction. Of course, a living tree and the branches are always in bending. And I don't know why the living tree was invented, because branches in bending needs most of material. But living nature is not invented for a certain goal. When a thing is in living nature, it is then developed and developed. But if you will, but you can use this type of structure when you are, especially when you are put them in compression. The model on the left side I made with my students at Yale University, 1960. It was hanging like the Gaudi model, little wire, not wires, very thin threads, which we bound together and then stiffened with polyester, just make it wet with polyester, and we could help the model in taking an upper plate. We with this type, we made then in the late 70s a large project for Saudi Arabia, especially for the Council of Ministers and the new chamber of the new parliament called Majlis al-Shura, and we have had some good ideas. And the models has been done in Germany in my office. The calculation in Stuttgart for the Majlis in a joint venture between OFI Arab and Bureau Apple. And we have been sorry we could not build it because King Khaled died before. But we used the method then for our second version of the magnetic railway on the right side. And in this time, Norman Foster used this thing a little bit in a little different way, but the method of calculating for the new London airport, Stanford. Yeah. Next picture, and a very peculiar thing. This was the tree structure for the Parliament of Saudi Arabia, which we did not build, but it was published. And now, and now, if you enter Stuttgart, you see our column there by a very well-known German architect and a very well-known German engineer. The only trouble is they did not ask us. But Rolf Gutbrot, before he died, rang me by telephone, said, last not least, we have from the huge project for Saudi Arabia, it was a governmental building, at least a little piece standing. Next picture. But you can use the method also for a very small thing with not real functions. I made a little sculpture for a poet in our village, and is a well-known German poet, always making poems for the nature, and so I have given him this type, a real tree where water drops are coming out, falling in the basin, which is the old fountain of the village. Next picture. Lightweight structures can get lighter and lighter. And the lightest one is the thin membrane, but when you are working with new type of structures on the left membrane, and it was 32 to 28 meters large, and we made the shape in reality like the model and push it with hydraulic power and was getting this shape. We used for the left structure, it was in Berlin, 1957, a new material, a polyamide fiber called Perlon, similar to nylon. But what happened, the fiber was not good enough in ultraviolet light, and so the structure did open. It had a so-called tearing. The owner of the restaurant rang me. It is just beside the palace of the German president, just behind the structure stands in Berlin, and said it was wonderful, it did open. But Peter Strohmeyer, in 14 days I have had a new skin. On the right side, it was, I'm a member of the German Academy of Arts, Berlin. It is the oldest institution for arts, 300 years old, and for the festification, which